So hi everyone, my name is John Tarafa, and in this video I will be showing you how to do Fluent Project One and the Fluent Ansys program. Ansys Fluent. Okay, so once we have the program open, we want to use the Fluid Flow Fluent. Here it is. We select the Fluid Flow Fluent. And then our next step is actually creating the geometry. So we want to open that tab up. I believe I have it opened over here. Let me show you guys actually. Okay, here it is. So what we first did was actually create the circle that we have here. This is the cylinder wall. We actually ended up using this circle. First of all, this is a 2D project. Let me zoom out a little bit. So when you first open this program up, it's going to open up as a 3D project. We want to hit on the Z coordinate to convert it to 2D, which we actually use for this project. So we first did the circle here, and then we used 4 rectangles as a control volume around the cylinder. We placed four squares, and this is our control volume over here. See? Okay, I believe that's it for the geometry. We go to workbench. And now our next step is the meshing process. Let me show you guys what mesh looks like. Meshing. Okay, here it is. So for the meshing section, we obviously use the surface body as a meshing section. We use Y and X coordinate system because it's a 2D. And then we actually use the all triangles method. We use the edge sizing for the cylinder wall, and then the inflation. Then the next step was actually naming the selections. We named on the far left of the velocity inlet, and we actually used the velocity inlet of 10 meters per second for this project, but you can change it. I believe you can change that in the setup section. This is the pressure outlet. This is the cylinder wall. And these two walls, actually, this wall and this wall is actually the symmetry walls. So after you're done naming your sections of your figure, you can head out of the meshing section back to your workbench, and you can start on step 4, which is your setup step, which in here, this is where you get your calculations and all sorts of stuff. So let me screen share that. Okay. So in here, once you open up here, you're not gonna have any of this. Let me see if I can just close this. Your figure should be popping up here. I don't know why mine is not popping up, but your figure should be popping up here. And then you want to once you actually open up your models tab, you see that you have plenty of choices here. And here you click on your viscous, and you can change it from inviscid to laminar. And this one, Spalaris, is actually turbulent. So it just depends on what you want to run it. But for this, since I already have it here, I'm going to use turbulent flow just for the demonstration of this video. I'm going to use a turbulent. Okay, so once you have it set to turbulent, you have your energy equation on. You want to, only for laminar and turbulent flow, you want to have your energy equation on. For inviscid flow, you want to turn the energy equation off. Okay, so we go to fluid. No, that's actually the cell zone conditions to change the viscosity and the density to match the Reynolds number. Okay, so we come to the surface body. You see the material name, we have air, and then you want to click on edit so we can edit these values. You see, so in here, you see we have the density and we have the viscosity, which we can both change to match the Reynolds number. You see, in this equation, or in this, how do you say, in this step, since we're using the turbulent flow, we actually matched the density and the viscosity to match the 800,000 Reynolds number. So we click on, so after we're done that, we close it up. And then we're done with that. We already set up. That's pretty much the hard part of this project. Actually setting it up to match the Reynolds number. Okay. So now we want to initialize the problem so we can actually start our calculations. So for this project, we used the hybrid one with 35 iterations. You can do more, you can do less, but for this project, 35 is the one to go along with 1,000 iterations. So we click on initialize, and as you can see, it's doing the iterations here. Now you want to wait until it's done. And you see, hybrid is done. So once you've done that step, you want to actually run the calculation. That's the next step. Now for this project, we use 1,000 iterations, but for the demonstration of this video, we're gonna do 25 iterations just to make it a little bit faster, so the whole video is not actually doing the entire iterations. So we want to calculate, and as you can see, it's a little bit slower. That's why I'm only doing 25 of them. See, here's the scaled residuals. You see, and now it goes one by one for the iterations. And now this step is just pretty much waiting until all of the iterations have been done. Okay, it's almost done. Okay, calculation complete. Okay, so once we've actually done the iterations, the calculation is done. Now it's actually, we got to do what the project is asking us to do. And the first step of the project that was asking us to do was to find the velocity contour and the pressure contours. So we go over here to the results tab. We click on contours, and this is the pressure contour. And we want the contour of everything. You have to click this, contour lines, click compute. See, here's your min value, your max value, and then display. And here is, let me move this out of the way. And you see, here's your pressure contour. See, not much changing since it's a turbulent flow. You have a little bit changing over here. See, you can zoom in and out. Okay. Okay, so that's the pressure contour. And then we want to find the velocity contour as well. You click compute, display. And here's your velocity contour. Let me move this out of the way just so you can see it better. See, there it is. So once you have those two contours, the next step of the project was to actually find a streamline of the project. So to find the streamline, you have to go back into the workbench, and you gotta hit step 6, results. That's where the streamline is at. Let me open up the results tab. Nope, that's not it. Okay, here it is. Let me show you guys. Okay. Yes. Okay, so once we're over here in the results tab, you see this is the velocity streamline that we calculated. But to actually find the streamline, it's actually this icon over here. This little icon, you click on this little icon, and it should show you the streamline that it was calculated. See? It's a pretty good streamline around the cylinder. Okay, so once we have that, the next two steps, it's actually done again on the setup tab. So let me go back to the setup tab. Okay. And the last two, actually the last four, is the pressure coefficient, the velocity distribution. These two are done on the plots. We go to X and Y plot. You see, we have the pressure over here. We want to do the pressure coefficient, and we want to do it over the cylinder wall. Now we save and plot. And there's your pressure coefficient right there. Now, if we want to do the velocity distribution, we click on velocity, save and plot. And there's your velocity distribution. Now, the last two steps is actually finding the drag coefficient and your lift coefficient. And the way we find these two, I believe they're on reports, yep, and on forces. You see, we put this to 0. And in order to find the drag coefficient first, we need to change the X to 1 and leave Y and Z to 0. You see? So now we click print. Let me see if I can make this a little bit bigger. Let me move this out of the way. Okay, so you see here, we have the direction vector of 1, 0, 0. This is for the drag coefficient. And you see we have the forces pressure, we have the viscous, we have the total. And here are your computer values for the drag coefficient. Now, if we want the lift coefficient, the only thing we need to change is the direction vector. We need to put 0x and then 1 and the y. Click print. And here are your lift coefficient values. See, the direction vector changed, 0, 1, 0. And here are your computer values for the lift coefficient. Okay, so pretty much for this project, that's all the things that were calculated and needed to be done. And again, for this project, we did it as in turbulent flow, actually. In order to change it, here's inviscid, here's laminar. Another thing that was done for the laminar flow, only for the laminar flow that was done, we actually had to add a moving wall for the laminar flow. So once you change it to laminar, you again adjust your density and your viscosity values to match your Reynolds number of the laminar. After you've done that, you go to your wall, you go to cylinder wall, and as you can see, we first do it as a stationary wall. You run your calculations, you get your plots as your stationary wall, and then we want to have a moving wall. And the first value that we did was -20 radians per second. We want to do it rotational. And now the reason why we add a negative sign in front of the value is because in Ansys Fluent, I believe counterclockwise is actually positive and clockwise takes it as negative. So we want to do the rotation in the clockwise direction. So that's why we need to add a negative sign in front of the value. to make sure it's accounted that it's going in the clockwise direction. So once we do that, we again run our calculations, get our plots for the moving wall of -20 radians per second. After we've done that, we change it to -40, apply, close. And then again, we run our calculations and then we get our results. And that's pretty much it, what we had to do for this project. I believe I'm not missing anything. It was a pretty simple project if you understand the program. You know, just getting some plots here and there. But other than that, that's pretty much it. Thank you guys for watching this video.